Hey everyone, today we will be presenting our work on sandboxing Libopus in Firefox, things that we learned along the way, and some performance results. So firstly, why do we care about this? Most major web browsers rely on third-party libraries, and as we saw in one of the earlier papers in the quarter on software fault isolation by our TA Shravan, we can see how important it is to ensure that any compromise in a third-party library does not affect the entire browser. We chose to focus on the Libopus audio decoding library, which is widely used on many streaming and video platforms, including YouTube. So really, we wanted to sandbox this library to provide an additional layer of security in the event of a compromise and implement software fault isolation from a practical perspective, seeing how it impacts performance in a real-time application. A bit more about the Opus library. So it's an open source library that has been around for several years. And like I mentioned, it's supported by many browsers and commonly used for audio file sharing. So some of the key features are that it supports a relatively wide range of bit rates compared to other audio libraries, and it has low latency. We want to maintain very fast decoding times with Opus while implementing our fault isolation. So it's key that the latency overhead of the sandbox implementation is low to the point that there is little to no perceivable delay in the actual audio decoding. So with that, I'll pass it on to Ayush, who will talk about the approach that we took for our implementation.
Coming to the approach we followed, we first referred to the existing sandboxing implementation done for libogg and Hunspell. It helped us get acquainted with the code structure, conventions followed in Firefox, and how we could go about sandboxing libopus. We relied heavily on the Opus API documentation to determine pointers being passed out parameters and the return values. With that, we started making changes incrementally to reach no-op sandbox. One thing that we kept in mind was to try a build after every change. With no-op sandbox done, we tested the audio decoding functionality and we found our changes had caused an issue. I'll be going over that in detail later on. Once we fixed the issue, we worked in parallel to write verifiers and switch sandboxing to the WASM mode. Verifiers were written based on expected values that the out parameters or return values should be. With WASM mode enabled, we tested it again on YouTube and Opus audio files and moved on to measuring performance impacts because of our changes. We'll be going over the performance measurements in detail later on. Next, we have a short demo of us playing a video on Firefox with and without WASM sandboxing done for Libopus. As you could see, there was no difference in the audio quality with and without sandbox. Coming to the challenges, we highlight three of them. The first one was we were getting a build error every time we sandboxed the function Opus multistream decoder CTL. The other function sandbox were not throwing an error. It was only after a certain point of time that we realized that maybe because it had a variable number of arguments that it was throwing an error. The RL box does not support functions with variable number of arguments. As a result, we added two wrapper functions in libopus to work around and move ahead in the project. The next one was a bit more complex, the one I mentioned before. With no-op sandbox, when we tested audio decoding, it was being decoded, but there was a lot of noise. As a result, we had to incrementally unsandbox every function to determine the specific function causing the noise. We narrowed it down, and while we tried different things and were able to fix the issue in the end, we are unsure of the root cause. But in our opinion, it was because of a padding or alignment issue. We fixed it by using the copy constructor of the audio buffer in Firefox instead of doing a simple mem copy. The next one is related to the Firefox build system. It expects that all the sources will be available in alphabetical order. When we tried passing the same list being used for non-WASM build of Opus to the WASM build part, it threw an error that the list is not sorted, but works as expected when we build it with the non-WASM mode. We are yet to debug this issue completely, but in the interest of time, we worked around by adding a static sorted list of sources in the MOS build. With that, I hand it over to Link to take you over the performance measurements that we have done.
For the performance measurement, we're trying to look at it from these 5 metrics: CPU usage, RAM usage, time taken to decode audio, time taken for YouTube media, page load time with Opus Media, and our times at benchmarking the audio performance. So All of these tests are running on an Intel i7-857U CPU with 8 gigs of RAM, and the system is Ubuntu 2004. So this is our first matrix, the CPU usage. We use Adria, which is an open source software that allows us to do a detailed resource monitoring of applications, which basically monitors the PID of a process and tells us all the information we may need on that PID. In our case, we're trying to measure the resources used by the decoding processes, which accounts for almost 100% of the usage and should be good representation of the performance. So the next thing is quite obvious. We captured 20 iterations of the CPU consumption playing the same video and reported on the mean. The result is shown here. As you can see, there is no major increase on the CPU usage with the sandbox. Following is a RAM. The same methodology is applied to the RAM. We use Adria and 20 iterations of RAM consumption is captured and report on the mean. In this case, you can see there's on average like 2% increase from a no sandbox to a sandbox. The next thing we're trying to do is the time taken to decode the audio. Luckily, RLBox has support for this, and we're just using that. The decoding performance is tried on the Syntel sequence in SIF-aux media test suite, which Chevron used in his RLBox paper. To measure the performance on this, we first converted the original file to outputs with different bit rates and measured the time taken in sandbox for each file. And we saw approximately 100% overhead, which is consistent for all bit rates.
So the next thing that we measured is the decoding time for YouTube media. And what we observed was very much consistent with what we have already seen with Opus content on a static web page. That is a nearly 100% overhead while decoding within the sandbox. However, there was no visible impact for the end user as we have already seen in our demo. We attribute this overhead primarily to two reasons. First, we can no longer use the architecture-specific optimized Silk code since we now need to compile Opus into Wasm first, which will then be compiled into the architecture-specific code by the Lucid runtime. Also, with the Wasm toolchain being still in its nascent stages, the compiler-based optimizations are not as extensive as in LLVM. Another observation that we made was when a page with Opus media is loaded, sandboxes are created for a very short duration. So we decided to measure if our changes had any major impact on page load time and noticed a non-significant increase of around 3% in case of static web page, while an increase of around 15% for YouTube. We also performed a scale test that led to the creation of 250 concurrent sandboxes, but this did not have any significant impact on the CPU or memory usage or the page load time. Finally, we would like to talk about some of our attempts at benchmarking our changes. So one thing that we found out is that there is no standard benchmark for audio performance in browsers, and standards like PESQ cannot be used since they are more suitable for speech quality. Next, we made attempts to measure the bitrate of the audio playback using JavaScript, but found out that MOS frame delay, the API which is used for this in JS, has recently been deprecated. So with no API available to measure the audio bitrate, what we next tried was to create a blank video with Opus audio in it and use the video playback quality API. However, we observed that the total frames count field was only updated based on the video, and varying the audio bitrate did not have any impact on it. Finally, what we tried to do is to make use of the audio tests that are used in Chrome and see if they can be extended to Firefox. One such test is the mixed audio latency performance test, which we are still trying out. It measures how fast we can continuously repeat a short sound clip while another clip is running in the background. But we still need to check if this is applicable for benchmarking our project.